In this lesson, we're going to look at the unit circle, which is an important concept to understand as we move forward in trigonometry. The unit circle refers to a circle of radius length 1 that's centered at the origin. And we're going to take the special triangles that we know and superimpose them on this circle so that their hypotenuse lines up with the radius of the unit circle. Let's start with a 30, 60, 90 triangle. If this is my 30-degree angle and this is my 60-degree angle, then I know my sides are in ratio 1 root 3 to 2. Now I want to take this triangle and superimpose it here so that this is my 30-degree angle, this is my hypotenuse, and I form a triangle like that. Now I need to resize the triangle because right now the hypotenuse is 2 and this radius here is only 1. So I'm going to divide all of the side lengths in 2 to give me a hypotenuse of length 1. That means this side is length root 3 over 2, and this side length is 1/2. That makes this 1/2, and this root 3 over 2. Now we can see then that the coordinates of this point on the circumference of the circle at the end of the hypotenuse must be root 3 over 2, comma 1/2. Now let's erase some of this to keep things from getting too busy. And let's say that this angle now is 60 degrees. If this is 60 degrees, then we have another 30, 60, 90 right angle triangle here. Now again, if this is a hypotenuse of length 1, then this time this is my side length of 1/2, and this is my side length of root 3 over 2. That makes the coordinates of this point 1/2, comma, root 3 over 2. Now, if we carry on, again, I'll tidy this up a bit. This is a 45-degree angle. So I've got a 45, 45, 90 triangle. Remember, my 45, 45, 90 triangle had side lengths of 1, 1 and a hypotenuse of root 2, if this is 45 degrees. Again, though, I want to superimpose this here, and this is a radius of length 1. So I need to divide everything so that the hypotenuse has length 1. That means I need to divide by root 2. So now my hypotenuse is 1. My other side lengths are 1 over root 2 and 1 over root 2. So those go here, 1 over root 2, 1 over root 2. And that makes the coordinates of this point 1 over root 2, comma, 1 over root 2. So what we've got then is 3 points on the circumference of this unit circle, which we've worked out using our special triangles. Now what we're going to do is we're going to reflect each of these points across the y-axis and across the x-axis to figure out what the corresponding points are in the other quadrants. So I'm going to encourage you to pause the video now and work that out yourself. As an example, if we take this point here, remember this was 30 degrees, and we reflect it across the y-axis, then this, which we had been calling our related acute angle, is going to be 30 degrees. That means this is 150. And the y value will stay the same, but the x value over here is going to be negative. So pause the video now and go ahead and work out all the other points in the other 3 quadrants. So these are the values that you should have gotten. The x values are negative on the left half of the Cartesian plane, and the y values are negative on the bottom half of the Cartesian plane. So check your answers against these. Now let's look more generally at what's happening here. We're going to call this point at the end of this hypotenuse xy. And we can, again, draw a right-angled triangle so that this length is x, this height is y, and remember that the radius, or the hypotenuse here, is 1. Now remember that cosine theta is defined as x over r. Now in this case, if this is theta, r is just 1, so cosine theta is equal to x over r, which is equal to x over 1, which is just x. And similarly, sine theta, which is defined as y over r, becomes simply y over 1, or y. That means instead of writing the coordinates of this point as xy, we could write the coordinates of this point as cos theta, sine theta, where theta refers to this angle here, the principal angle. And we could do that for any of these triangles or any other triangle that we could draw on the unit circle. In other words, instead of defining the point as having the coordinates xy, we could equally well define xy on the unit circle as being cos theta sine theta. So the x value of each point on the circle is the cosine ratio of the principal angle theta, and the y value of each point on the circle is the sine ratio of the principal angle theta, just as we've seen here. If you go back to the values that we worked out, let's take a look at an example. If this is 30 degrees, this was cosine 30, and this is sine 30. It works in other quadrants as well. If this angle here is 60 degrees, then that makes this 120 degrees, and cosine of 120 is negative a half. Sine of 120 is root 3 over 2. So the unit circle helps us because each point on the unit circle, xy, can instead be thought of as cosine theta sine theta. Working forward from this, we know that by the Pythagorean theorem in any right-angled triangle, x squared plus y squared equals r squared, where r is the length of the hypotenuse. Now on the unit circle, x is equal to cosine theta, y is equal to sine theta, and r is equal to 1. So replacing x with cosine theta, y with sine theta, and r with 1, we get cos squared theta, and writing this squared here means the same as this. We've taken the whole cosine theta ratio first and then squared it. So cos squared theta plus sine squared theta equals 1. And often the way you'll see that written is sine squared theta plus cos squared theta equals 1. That's called the Pythagorean identity. It's an identity because it's true no matter what the value of theta is, and it's the Pythagorean identity because it's derived from the Pythagorean theorem. Okay, let's look at some of the things that we can think of with the unit circle. The unit circle can help us understand why neither sine theta nor cosine theta can ever be greater than 1 or less than negative 1. If we go back to our picture of the unit circle, this point here is the point 1, 0, and this point is negative 1, 0, and the point here at the top is 0, 1, and at the bottom is 0, negative 1. Now remember that cosine theta is just the x value on the unit circle, so x is never bigger than 1, and x is never less than negative 1. And it can take all the values in between as you go around the circle, or around the bottom. Sine theta is the y value on the unit circle, and it can never be less than negative 1 and still be on the circle, and it can never be greater than positive 1 and still be on the circle, but it can also take all values in between. So sine theta is equal to the y value on the unit circle, and the y value on the unit circle is always between 1 and negative 1. And cos theta is equal to the x value on the unit circle, and it's also always between negative 1 and positive 1. Also, you can see that as you go around the circle, the x and y values repeat. This x value of this point is the same as this x value of this point, and the y value of this point is the same as the y value of that point. So the x and y values repeat, therefore the sine theta and cosine theta values repeat. So x and y repeat as you go around the circle. Another thing that we can use the unit circle for is working out the sine, cos, and tan ratios of things that don't fit in right-angled triangles, just as we started to do in the previous lesson. So sine theta, remember, is equal to the y value on the unit circle, cos theta is equal to the x value, and tan theta is equal to sine theta over cosine theta. So asking what the sine ratio of 0 is, or sine 0, is asking what's the y value on the unit circle when you've moved 0 degrees. So if we go back here, once you've moved 0 degrees, your y value obviously is 0, so this is going to be 0. Sine of 90 is asking what's the y value when you've gone 90 degrees. That's at the top of the circle, so that's going to be 1. 180, sine of 180, the y value there is at the other side of the unit circle on the negative x-axis, so it's going to be 0, and 270 is at the bottom, so the y value there is negative 1. Cosine theta, now we're asking for the x value. When theta is 0, you're at the point 1, 0, so the x value is 1. When you've gone up to 90 degrees, the x value is 0. Over to 180, the x value is negative 1. And down at the bottom, the x value is 0 again. For tan theta, we want to take sine theta divided by cosine theta. So 0 over 1 is 0, and 0 over negative 1 is also 0. But 1 over 0 is undefined. And negative 1 over 0 is also undefined. So tan theta is undefined for theta is equal to 90 or 270 degrees. Another thing that you can do with the unit circle is use the Pythagorean identity to solve problems. Here's an example. If sine theta is equal to 2/3 and theta is between 0 and 360 degrees, find cosine theta. Now the Pythagorean identity tells us that sine squared theta plus cosine squared theta is equal to 1. And we know that sine theta is equal to 2/3, so 2/3 squared plus cosine squared theta is equal to 1, or cosine squared theta is equal to 1 minus 2/3 squared is 4/9. So cosine squared theta is equal to 5/9. Square rooting both sides, we get cosine theta is equal to, remember to take the positive and negative square root of 5 over 9, or simplifying that, we get cosine theta is equal to the positive or negative square root of 5 divided by 3. Notice that we never had to solve for theta in order to find cosine theta. Also notice that we got two different answers, one positive and one negative. If sine theta is positive, we know that we're in the top half of the Cartesian plane by the cast rule. But there's two possible answers up there, one in the first quadrant, one in the second quadrant. In the first quadrant, cosine will be positive, that's where the positive answer came from, and in the second quadrant, cosine will be negative, that's where the negative answer came from. So that's an introduction to the unit circle and the kinds of problems that it can be used to solve.